Solving longest mountain in array problem using dynamic programming. That's what we are going to do in this video. Welcome my friends to Joystick. I truly recommend that you watch this video till the end because not only you are going to add one more DP problem to your bucket of problems, but you are also going to feel a sense of accomplishment once you have completely understood the DP algorithm to solve this problem. Alright, what are we waiting for? Let's see the problem statement. So you are given an array of integers ARR. This is the array that we are going to use in our problem. You need to return the length of the longest subarray, which is a mountain, and you should return 0 if there exists no mountain subarray. But what is a mountain subarray? Let's find it out. Okay, first of all, a mountain array has a length equal to or greater than 3. That means an array can be called mountain array if it has 3 or more than 3 integers. The second is, in a mountain array, there has to be an element ARR I that is greater than all the elements previous to it on the left hand side, and ARR I should be such that it is greater than all the elements next to it on the right hand side. These three are the properties of a mountain array. In this array, if you see, the longest mountain sub array is this. Check here, we have 7 which is greater than 1 and 4 that exist on its left hand side, and on the right hand side we have 3 and 2 from which 7 is also greater. This sub array forms a great mountain as well. Now you understand what a mountain sub array is? Okay, so let's solve this problem now using the DP technique. The solution to this problem struck me quite easily, but how? Because it is the same as the temple offerings problem that I have already solved before. You can find the link to the video in the I button, or you can find it in the description box of this video as well. The key to solving this problem is to understand that 7 here, or the peak of a mountain sub array, is greater than the integers on the left, and the same peak is greater than the integers that are on its right. So first we are going to trace this array from left to right, and then we are going to trace this array from right to left. Thus we create an array of the same size and we call it left. Initially we fill it with zeros. This array will store the number of integers a particular integer is greater than that are on its immediate left. This is like recording from the point of view of a particular integer how many integers on the left hand side it is greater than in a continuous manner. Every integer that we consider will act as the peak of a mountain. We start from this cell at index 1, and assuming it as the peak of a mountain, the algorithm will check if the integer here, which is 1, is greater than the integer in the previous cell, which is 2. So is 1 greater than 2? No, thus nothing happens and we move to the next cell. 4 is the value of the cell at index 2. 4 is greater than 1. So what the algo will do over here is it will add 1 to the value stored in the cell at index 1 of this array left, okay, which corresponds to this value 1 obviously, and it's going to store the result of the addition of 0 and 1 in this cell. What does this mean? It means that there is one integer that is less than this integer 4, and that is on its immediate left. The algo moves to the next cell. Here the integer is 7 and 7 is greater than 4. What's the value in the corresponding cell of the left array over here? It is 1. So we add 1 to this one, we get 2, and we populate 2 in this cell. What does this indicate? 7 is greater than 2 integers that exist on its immediate left in a continuous manner. And check, it took help from the value stored in this subproblem. That's what dynamic programming is. The algorithm now moves to 3. Is it greater than 7? No. 7 is on its immediate left, but 3 is not greater than 7. So the value over here in this cell remains 0. Alright, as the dynamic programming algorithm, we move to this cell. Here the value is 2. Now 2 is not greater than 3, which is on its immediate left. So no change we make here in this value in the corresponding cell of the left array. It stays as 0. Remember, this says that 2 is not greater than a single integer that exists on its left in a continuous manner, or that exists on its immediate left. Finally, the algorithm comes to 5. 5 is greater than 2. So we add 1 to the value that exists in the corresponding cell of the left array, which is 0 obviously. Thus we add 1 to 0, we get 1, so we populate 1 in this cell. This means that 5 is greater than one integer that exists on its left in a continuous manner till 5. Since it's a sub-array that we are looking for, that is why in a continuous manner term is very important to keep in mind. Alright, the entire left array is filled. Now we create another array and we call it right. This array will store the number of integers a particular integer is greater than that are on its immediate right. This is like recording from the point of view of a particular integer how many integers it is greater than in a continuous manner that exist on its right hand side. So we are going to start from this cell that happens to be the second cell from the right hand side. What's the value over here? It's 2. Is it greater than 5? So the value in the corresponding cell of the right array stays as 0. We move to this cell now, which has the value 3. Is 3 greater than 2? Yes, it is. So what we are going to do, we are going to add 1 to this value, which is 0, stored here in this cell of the right array. The result of the addition of 1 and 0 comes out as 1, which we are going to populate in this cell. And what does this indicate? That 3 is greater than one integer that exists on its immediate right. Okay, now the algorithm moves to this cell. Here the value is 7. 7 is greater than 3. And what's the value that exists in the corresponding cell of the right array? It's 1. So we add 1 to this one, we get 2. And that we populate in this cell. Take a look over here. Again, I'm saying this number 2 indicates that 7 is greater than 2 integers that exist on its right. And the algo took help of this value calculated as a part of this problem to come up with this value 2. And that's what dynamic programming is. Now we move to this cell. Here the value is 4. Is 4 greater than 7? No. Since it is not greater than 7, hence we calculate no value over here, and the value in this corresponding cell of the right array stays as 0. Then the algo moves to this cell where the value is 1. Since 1 is not greater than the integer that exists on its immediate right, hence we do nothing over here. The value in the corresponding cell of the right array stays as 0. And finally the algo reaches this cell where the value is 2. Since 2 is greater than the integer that exists on its immediate right, hence what happens? We add 1 to the value stored in the corresponding cell of the right array of this integer. The addition of 1 and 0 gives us 1, so we populate 1 in this cell of the right array that corresponds to the integer at which algorithm is right now. Alright, so the right array is full as well. Now here's the best part. We need to add the values of the corresponding cells together of these two arrays only where neither of the cells contains 0. Okay, let's do that first and then I'll explain why we did that. Okay, so we have added up the values of the corresponding cells of these two arrays left and right. Why we didn't add the values of the corresponding cells of these two arrays where even one cell contained 0? Because having a cell 0 in either of the arrays eliminates the possibility of having either smaller integers on the left or on the right. Okay, so we see there is only one value that emerges as a result of the addition of the corresponding cells of these two arrays. What does this 4 say? It is actually the length of the longest mountain excluding the peak element, which is 7. So 7 is the peak of the mountain. It is greater than 2 integers on the left and it is greater than 2 integers on the right. 2 plus 2 is 4. That's what we are getting over here in this cell. So the only thing remaining is to add 1 to this 4. This one is for the peak, which is 7. We get 5 as the output. And this 5, my friend, is the length of the longest mountain in this array. If you are interested in looking at the Java program that implements the TP algorithm to solve this problem, longest mountain in array, then you should definitely visit my GitHub link, which you can find in the description box of this video. With this, we have come to the end of this video. I hope you enjoyed learning to solve this problem, longest mountain in array, with me. Do let me know in the comment section if you got any doubts related to the solution of this problem. Do let me know in the comment section how you find the explanation. I'll see you in the next video of Joey's Tech. I look forward to helping you with programming and algorithms, and only for this video. Goodbye.